This is a picture, and this is a video. You can probably already see what is the difference between a video and a picture. But do you know what a video is? Video is a series of images or frames sequenced through a predetermined interval and then synced with sound to produce a certain narrative. Let's take a look at an average image size like the one you saw earlier. That screenshot that is taken from my computer has a size of around 1.01 megabytes, and assuming all frames are the same and we have 60 frames in a second and the video length is about 2 minutes and 1 second, we can expect the size of the video to be around 7.3 gigabytes. But in reality, the size of the video in my computer is only 33.6 megabytes. So how is this possible? You probably already know from the previous videos that the answer is compression. You probably already established that there are two types of compression, which is lossy and lossless. With lossless aims to maintain the highest amount of quality with a sacrifice on storage and memory. But as you probably already see, the size of the video on my computer is significantly smaller than our theoretical size. So lossless compression just won't cut it. We need more compression but without sacrificing too much quality. Based on that parameter, we already have several guidelines for our compression method, which are lossy but still preserve quality and can run at a high bit rate to compensate the loss of quality from our compression. An average video compression has two types of compression at play, which are intra-frame or spatial compression, which is a compression on a single frame of video, and interframe or temporal compression, which is a compression between frames. Intra-frame compression is basically just image compression, because you probably already heard intra-frame compression is just a compression of a single image or frame. In interframe, however, it is a whole different story. We use something called codecs, which is short for coder and decoder. The most notable and most widely used codec right now is MPEG-4 or H.264 codec. There are two components of H.264 or MPEG-4 codec, which are closed-loop encoding and motion compensation. Let's take a look at them one by one. The first is closed-loop encoding. A closed-loop encoding is a technique that uses feedback from the output of a video encoder to adjust the input and improve the performance or accuracy of the video encoder. Think of it like using the feedback from the GPS and the map to adjust the route and the speed of the car. For example, if the GPS detects the traffic or a road closure ahead, it can suggest an alternative route or a lower speed to avoid delays or accident. In a closed-loop video encoder, the reconstructed frame or the output of the encoder is sent back to the encoder and used as a reference for predicting and encoding the next frame or the input of the encoder. This way, the encoder can reduce the errors and artifacts that may occur during the compression process. And then the second component in an MPEG-4 codec is motion compensation. Motion compensation is a technique that predicts the frame in a video based on the previous frames by accounting for the motion of the camera or objects in the video. This reduces the amount that needs to be encoded and transmitted for video compression. Imagine motion compensation like using the motion of the car and the map to predict the next location and direction of the car. For example, if the car is moving at a constant speed and direction, the navigation system can predict where the car will be in the next few seconds or minutes, and display the relevant information on the screen. Similarly, motion compensation uses block matching algorithms to find the best match between a block of pixels or macro blocks in the current frame and the shifted block of pixels in the reference frame, and then encodes the difference between them. Here is a simple diagram that portrays the compression process using a closed-loop encoding. Let's say we already have a decoded frame n that is passed from the cycle above, and then we use the motion compensation to produce a prediction of the frame n plus 1, as you can see on the left here. And then we compare that predicted image with the original frame, or we subtract the original frame with the predicted frame to produce what we call a residual frame. That residual frame then will be compressed and then quantized and then transmitted into the encoded image. This cycle is what we call a closed-loop encoding. And here is a short process of how video decoding works. Let's say we already have a current frame n on the left. Then we already have a motion vector that we stored in the data of the video. We then add the motion vectors to produce the predicted P frame. We'll talk about that later on. And then to improve the quality of the image, or to make it as close as possible to the original frame, we add that residual frame that we transmitted earlier. So the next frame, you probably cannot see it very clearly, but the transition is much more smoother and more similar to the original footage. Here is a short description of how the encoding and the decoding process works. As you can see, the purpose of this compression is to create a frame as close as possible with the original, but still maintaining a small size. You probably also heard that motion compensation has the same principle of video stabilization, but we won't talk about it in this video. So then, what are the end products of this encoding? The end product of this encoding is what we call the three frames called I, P, and B frame. Let's talk about the I frame first. I frames, or intra-coded frames, are complete images that can be decoded independently of other frames. They are used as reference frames for other frames in the video stream. I-frames are the least compressible frames and are used to restore quality and resilience. You can say that I-frames are basically compressed JPEGs because they are just a complete image with no way of compression whatsoever. Next is the P-frame. P-frames, or predict frames, are compressed frames that are predicted from the previous I or P frame. They contain only the changes in the image from the previous frame. P-frames are more compressible than I-frames and are used to improve compression efficiency. An example of P-frame here is my face cam. You can see that the cupboard behind me doesn't change whatsoever, and you can just tell the P-frame to let the background to stay the way it is. You don't need to save the footage of the cupboard again and again, you just need to save the information. On the other hand, my head that is moving needs to be compressed and save the motion vectors so that the size of the file can be decreased significantly. That is why the P-frame is here. Since P-frame is more efficient, you can say that P-frame is half the size of a normal I-frame. Last, we have B-frame. B-frames, or bidirectional frames, are compressed frames that are predicted from both the previous and the next I or P frame. They contain only the changes in the image from the previous and the next frame. B frames are the most compressible, and frames are used to further improve compression efficiency. Because B frame relies on the other two frames before and after it, you can say that the size of a single B frame is around a quarter of a single I frame, or half of a normal P frame. Here is a short diagram that shows the arrangement between I frame, P frame, and B frame. As you can see in the beginning, we have an I frame because there are no benchmark on how we need to display the image. Then we send in a P frame, which is located on the fourth fourth frame, the green one. P frame, as you probably already know, is a collection of information and commands for pixels to move around. So we can use that iframe to create a predicted image from the P frame. And then we add two B frames. They are basically the difference between the I and P frame. So the display orders are I1, B2, B3, B4, B5, B6, and so on. Because P and B frame relies on iframe, if you have a cropped footage like this, as you can see, there are no iframes here, but the P and B frames still predict and create a prediction image. But since there are no benchmark or the normal iframe, the motion is still conveyed, but the footage is shadowy, as you can see right here. That is all from me. I hope you learned something new. Thank you, and I'll see you in the next video.